Hi children, welcome to another chemistry class. In this class, we are discussing, as you can find, unit 8, redox reactions. A very small, simple chapter from 11th standard topic, redox reactions. Are you ready? Can we start? Yes. So topic 1 is, what is redox reaction? All of you know what is redox reaction. It is a combination of oxidation and reduction. Redox reactions are a combination of oxidation and reduction. So oxidation reduction reaction, which always happens hand in hand. That is why it is called a redox reaction, known to all. Let me talk about the scratches from the beginning segment of the topic. What is oxidation? What is reduction? Conventionally speaking, oxidation means addition of oxygen. Oxidation means addition of oxygen. Addition of oxygen is called oxidation. Meanwhile, what is reduction? All known to all. It is removal of oxygen, or we can say addition of hydrogen. Addition of hydrogen is called reduction. So addition of oxygen is called oxidation. Addition of hydrogen is called reduction. Or we can have other traditional approaches. Addition of oxygen is oxidation, while removal of hydrogen is also called oxidation. So what about reduction? Reduction is just opposite. Everything opposite to what we comment here will be reduction. So addition of oxygen, oxidation. Removal of hydrogen, oxidation. Addition of an electronegative element. Addition of an electronegative element, that is oxidation. Then removal of an electropositive element, that is also oxidation. So addition of oxygen, removal of hydrogen, addition of electronegative element, removal of electropositive element. These are the classical definitions of oxidation known to all. According to the modern reviews, oxidation is to be understood as, oxidation is nothing but losing of electron. Losing of electron is called oxidation, or we can say an increase in oxidation number. An increase in oxidation number, that is called oxidation. These are the definitions of oxidation. The first four we can call it as classical idea of explaining oxidation, while the last one is electronic modern review. So what are oxidation? Adding oxygen is called oxidation. Addition of hydrogen is called reduction. Oxidation. Addition of oxygen called oxidation. Removal of hydrogen called oxidation. Addition of electronegative element called oxidation. Removal of electropositive element called oxidation. Losing of electron called oxidation. Hence, increase in oxidation number called oxidation. Everything opposite will be called reduction. So what about reduction? Number 1, it was written addition of hydrogen is called reduction. Then what about that? Removal of oxygen. Removal of oxygen is called reduction. Addition of oxygen called oxidation. Removal of oxygen called reduction. Then addition of electronegative element called oxidation. Removal of electronegative element. Removal of electronegative element, that is called reduction. Removal of electropositive element called oxidation, while addition of electropositive element called reduction. Losing of electron called oxidation. What is reduction? Just opposite. Gaining of electron called reduction. Increase in oxidation number called oxidation. What is reduction? Decrease in oxidation number. Decrease in oxidation number. That is called a reduction. These are the classical as well as electronic concept of oxidation and reduction. One to one, mutually opposite. Without oxidation, there is no reduction. Without reduction, there is no oxidation. Hence, it is called a redox reaction, which goes hand in hand. Okay. And all reactions are redox reactions. True or false? All the reactions are redox reactions. Is it true or false? It is a false comment. There are redox reactions and there are non-redox reactions. That may be a primary duty you are able to identify. 4 choices given to you. Identify which among the following is not a redox. Which among the following is a redox. Just for example, if you take up reaction like this, HCl plus NaOH giving NaCl plus H2O. Everyone know there is absolutely no change in the oxidation number of any element in the species in the reaction involved. That is, it's not a redox reaction. This is not a redox reaction. Why? Because you have H plus and you have H plus. You have Cl minus, you have Cl minus. You have Na plus, you have Na plus. You have oxygen minus 2, you have oxygen minus 2. You have hydrogen plus 1, hydrogen plus 1. All elements maintain their oxidation number same. There is no difference in the oxidation number. There is no electron gaining, there is no electron losing. This is not a redox reaction. Right? Meanwhile, the reaction between zinc solid plus copper sulfate aqueous, you are getting copper solid plus zinc sulfate aqueous. Everyone know this is a redox reaction and the typical example of galvanic cell. Right? What is happening here? What is happening here? Zinc elementary state 0 is oxidized to 2 plus. Zinc undergo oxidation. And any species undergoing oxidation is called a reducing agent. Zinc acts as a reducing agent and the reaction is oxidation. While copper 2 plus is converted to copper 0, that is a reduction reaction. So copper sulfate Cu2 plus undergo reduction and is called a oxidizing agent. A species undergoing reduction is called oxidizing agent. A species undergoing oxidation is called reducing agent. So here zinc is reducing agent, also called reductant. While Cu2 plus is oxidizing agent, also called oxidant. This is oxidation and this is reduction. This is an example, typical example of redox reaction. Right? So there are chemical reactions which are redox, which are not redox. That may be the primary responsibility to identify the nature, whether it is a redox reaction or not. Okay. Also, you need to understand the one which is oxidized, one which is reduced. The one which is oxidized is called reducing agent. The one which is reduced is called oxidizing agent. Right? Now, another typical example, let me tell you. You see that Fe2O3 plus aluminium giving Al2O3 plus iron, not a balanced equation. What I try to tell you is, you see, aluminium oxygen is added, that is called oxidation, or electronically you can say aluminium 0 turn, aluminium 3 plus, increase in oxidation number. So either classically oxygen added oxidation we can say, or increase in oxidation number we can say electronically. Both are binding to each other. Try to understand. Whereas iron oxide loses oxygen, that is reduction. Losing of removal of oxygen is called reduction. Even it can be complemented with the electronic content. This is iron 3 plus is reduced to 0. So here which is the oxidizing agent, which is the reducing agent? The one which undergo oxidation, aluminium is reducing agent, that is reductant, while iron oxide is oxidizing agent, that is oxidant. These are the elementary idea regarding redox reaction. You must be able to identify the one oxidation redox reaction and the one which is not a redox reaction, primarily starting from the chapter. So what is oxidation, what is reduction, what is redox reaction, which all reactions are not redox reaction, that will be the primary idea from the chapter. Now there are variety of redox reactions. Variety of redox reactions are there. If you take up a reaction, you see the simple example, hydrogen plus oxygen, you are getting water, 2H2 plus O2 giving 2H2O. This is a redox reaction where hydrogen 0 is converted to +1, that is oxidation, and oxygen 0 that is converted to -2, that is reduction reaction. This is a typical redox reaction and we call it as synthesis type of redox, combination type of redox. Two elements combined to give a compound. This is a combination type redox. This is combination type redox. Combination type or synthesis type. What about another type of redox reaction? Suppose we take up the reaction, say ammonia is converted to N2 plus 3H2. 2 ammonia decomposing to N2 plus 3H2. This is also redox reaction, but this is called a decomposition type of redox. This is decomposition type redox. Decomposition type redox, where you can understand, mostly all of you may be aware of hydrogen plus 1 is converted to 0. So plus 1 hydrogen moving to 0, that is reduction reaction. Nitrogen minus 3 converted to 0, that is oxidation reaction. From ammonia, nitrogen is oxidized to elementary nitrogen. Hydrogen is reduced to H2 gas. This is a redox reaction which is so called decomposition type redox. So redox reaction may be combination type, may be decomposition type. And another type of redox reaction which already we have seen, once I have written, let me write once again, zinc solid plus copper sulfate aqueous giving Cu solid plus zinc sulfate aqueous. This is a redox reaction. This is called a displacement type of reaction. Displacement type of redox reaction. Displacement type. And displacement, there are two types. One is metal displacement, one is non-metal displacement. This is a metal displacement reaction. Metal displacement reaction. Copper sulfate, from copper sulfate to solution, copper is displaced by zinc. That is a metal displacement reaction. And I have told you already, this acts as a reducing agent. This acts as a oxidizing agent. So this is a displacement type reaction, particularly called metal displacement. Why? Because there is another type of reaction, non-metal displacement type reaction. Suppose we take NaCl solution. Suppose we take NaCl solution in a test tube. And imagine I am passing F2 gas. An yellow colored F2 gas I am pumping into that solution. You can see a greenish yellow colored chlorine gas is evolving from the solution and the solution turn NaF aqueous. This is a displacement reaction, but this is called a metal displacement reaction. This is a redox reaction, metal displacement reaction. This is a redox reaction, displacement reaction called a non-metal displacement reaction. This is a non-metal displacement reaction. As here a metal is getting displaced, here a non-metal chloride is getting displaced. And what is happening? Hope you easily understand. Chlorine -1 is converted to 0. So chloride is oxidized by fluorine. Fluorine is a powerful oxidizing agent. Fluorine is a powerful oxidizing agent which undergo reduction of its own and is converted to F minus. So F2 easily converted to F minus. That means it undergo reduction and act as a powerful oxidizing agent, and that oxidizes chloride to chlorine. So this is oxidizing agent and chloride is reductant, reducing agent. And this is an example for non-metal displacement reaction. So this redox reaction can be combination type, redox reaction can be decomposition type, redox reaction can be displacement type, in which it can be metal displacement, it can be non-metal displacement. These are variety of redox reactions. Not over. A typical another example for redox reaction is, all of you know something special, where Cl2 when taken in alkaline solution, you are getting Cl minus and OCl minus. You get a chloride and hypochlorite. You get chloride and hypochlorite. And see what is happening here. Chlorine 0 is reduced to chloride. Simultaneously, it is oxidized to hypochlorite. Chlorine is +1 state. In hypochlorite OCl minus, chlorine is in +1 state. So from 0 to -1 reduction, from 0 to +1 oxidation, there is a simultaneous oxidation and reduction happening in certain species like this. This is called a disproportionation reaction. Disproportionation reaction. Disproportionation reaction. A species undergoing simultaneous oxidation and reduction. That is called a disproportionation reaction. Another example, say copper Cu plus is undergoing a change, Cu and Cu2 plus. This is reduction reaction, while this is oxidation reaction. In aqueous solution, cuprous ions are disproportionated to get cupric and copper. This is a disproportionation reaction. Going to organic chemistry, we have a very famous example for disproportionation reaction. I think many of you remember. Many of you remember that kind of disproportionation reaction. 2HCHO, formaldehyde taken in strong alkaline, concentrated alkali solution. You get CH3OH and HCOOH. Formaldehyde is reduced to methanol and oxidized to methanoic acid or a salt of methanoic acid. Hope you remember the reaction. Cannizzaro reaction. Cannizzaro reaction. This is called a Cannizzaro reaction. A popular example for disproportionation reaction. More formaldehyde is simultaneously oxidized and reduced in the reaction. So there are variety of examples for disproportionation reaction, and there are variety of reactions which are various kind of redox reaction: combination type, decomposition type, metal displacement type, non-metal displacement type, disproportionation type, right? There can be a reaction like this. There can be a reaction like this: 2PbSO4. 2PbSO4 converted to Pb and PbO2. A reaction like this: 2PbSO4 converted to Pb and PbO2. This is something special which you can understand. Lead 2 plus is converted to lead 0. Lead 2 plus is converted to lead 0 and lead 4 plus. Lead 2 plus is converted to lead 0 and lead 4 plus, PbO2. Now, what is the reaction happening here? 2 plus reduced to 0. 2 plus reduced to 0. 2 plus oxidized to 4 plus. 2 plus oxidized to 4 plus. This is an example for disproportionation reaction. Hope you easily understand. 2 plus is reduced to 0 and 2 plus is oxidized to 4 plus. This is a reaction happening in lead storage battery where the reaction during discharging is Pb plus PbO2 with the sulfuric acid. You are getting PbSO4. I was just this is disproportionation. Already we have discussed. This is disproportionation reaction. Now look at the discharging reaction that is originally happening in the lead accumulator, which is just opposite to the previously written reaction. You see the speciality for that reaction. What is happening here? Pb0 is converted to Pb2 plus oxidation, and Pb plus 4 is reduced to Pb2 plus. Now the point is that the same element in two different situations, the same element from two different situations. One is Pb0, lead 0, one is lead 4 plus, is coming to a common point, which is somewhat opposite to disproportionation reaction. Another type of redox reaction, which you call it as comproportionation reaction. Comproportionation reaction or synproportionation reaction. Comproportionation or synproportionation reaction. There are variety of types of redox reactions. Learning that is one important point from the chapter. Okay, understanding what is oxidizing agent, what is reducing agent, that is another important point. Moving on to the next topic in the chapter, that is finding oxidation number. Very important topic. How to find the oxidation number? Calculation of oxidation number. Calculation of oxidation number. What are the rules and regulations that drive you to find the oxidation number of various elements given in a molecule or in a species? You must understand certain facts which are known to all. What are the facts which help you to understand the oxidation number? Point number 1. Group 1 generally show +1 oxidation state. Lithium, sodium, potassium, alkali metals show generally +1 oxidation state. Generally means mostly. And group 2 always showing +2 oxidation state. Hydrogen always showing +1 oxidation state, while in hydrides it can be metal hydrides. It can be H-1 state. Metal hydrides. Oxygen usually we have -2, while in peroxides oxygen will be having -1 state, and in superoxides it will be having -1/2. Example, potassium superoxide. Potassium is +1. Oxygen is -1/2. Sodium peroxide, Na2O2. Sodium is +1 into 2 plus 2. Oxygen is -1 into 2 minus 2, like that. And quite naturally I can comment the sum of oxidation numbers. Sum of oxidation numbers should be equal to 0 for a neutral molecule. For a neutral molecule, the sum of oxidation numbers should come as 0 for neutral species or equal to the net charge. For example, if you take ammonia, the value for nitrogen and value for hydrogen. Nitrogen -3, hydrogen +1 into 3, it should come 0. While if you take carbonate, CO3 2-, carbon is +4 state and oxygen is -2 into 3. It should come this value -2. You can see +4 -6. It should come -2, the net figure. So the sum of oxidation numbers will be equal to 0 for a neutral molecule or equal to the net charge if it is a given anionic cationic radicals. That is another important point. Now the next one is usually halogens, fluorine, chlorine, bromine, iodine. Halogens will maintain -1 state. Halogens usually maintain -1 state, right? And especially fluorine only -1. Others normally -1, while in some molecules it can give up to +7 also, up to +7 also. So these certain regularized informations should be there in your mind when you try to work out the oxidation number. Say for example, if we are taking potassium dichromate K2Cr2O7, how to find the oxidation number of chromium? You must understand potassium is +1 into 2 and chromium we don't know, it is 2x. For one chromium X, there are 2 chromium. So I am giving 2x plus oxygen -2 into 7 is equal to 0. We know potassium alkali metal +1, oxygen usually -2 into 7. So what will be the value of X? It is +2 plus 2x minus 14 equal to 0. That is 2x equal to how much? 2x is equal to 12 and x equal to +6 you will get. So the oxidation state of potassium dichromate chromium will be +6 state, like that. And there must be as many examples as possible. You must try to practice, right? You must try to practice. Moreover, when some molecular structures are given, you can find the oxidation number. When molecular structures are available, you can find the oxidation number. How to find the oxidation number when the structures are given? You must have these sort of informations. Suppose there is AA single bond, the contribution is 0. Suppose there is AA double bond, the contribution is 0. Suppose there is AA triple bond, the contribution is again 0. Suppose there is AB single bond, this is -1, this is +1, provided B is more electronegative than A. Suppose it is AB double bond, it is -2 here, it is +2 here, provided once again B is more electronegative than A. Suppose it is AB triple bond, it is -3 +3. Suppose it is AB coordinate bond, it is -2 +2 dative bond. Suppose it is AA dative bond, it is -2 +2. Suppose it is BA dative bond, it is 0. Let me remind you, A and B are hypothetical elements where B is more electronegative than A. B is more electronegative than A. That context will also help you to identify the oxidation number. Particularly, there are so many scenarios when you encounter oxidation number paradox. That is oxidation number special cases when we encounter. Say for example, if you take CrO5, what is the oxidation state of chromium? A very popular example may be known to all who hearing the lecture. It is chromium, suppose we are giving X, oxygen -2 into 5 equal to 0, X -10 equal to 0, X equal to +10. This is mathematically perfect, but no element in the periodic table can have oxidation number 10. There is no element observed in the periodic table having oxidation number 10. And especially chromium, the maximum value is 6. That means whatever calculation is perfect, but the context is, the answer is wrong. What is happening there? The actual molecule, this is perchromic acid, which is basically maintaining this structural entity. This is the structural entity for perchromic acid. Out of the 5 oxygen, 4 oxygen maintain peroxide linkage. 4 oxygen maintain peroxide linkage. Now you see AB double bond. This is -2. This is +2. AB single bond -1 +1. 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 AA 0 contribution. So the total value for chromium come out to be +6, and now we are happy on the answer. So many paradox may be able to solve in using the oxidation rather than the conventional way of finding oxidation number using the molecular geometry if you know. Rather, using the molecular structure if available, you can find the oxidation number of any species. Okay, applying that one context which I have given as a note, applying this much information in your mind, you can find oxidation number of every species that is involved in a molecule that is given, asked to find out. For example, suppose you are dealing with acetic acid and they ask you to find out the oxidation number of entire species. Very simple. CH3 COOH. You see the context. This is AB +1 -1. AB +1 -1. AB +1 -1. So AB 0. So this carbon is having -3 state. Now coming to this carbon, AB double bond -2 +2. AB single bond -1 +1. So this carbon is having +3 state. So this carbon having -3 state, this carbon having +3 state, and if you go for average, it will be 0. It will be 0. And this oxygen again +1 -1. So this oxygen is -2, this oxygen is -2, hydrogen, all hydrogen +1, this carbon +3, this carbon -3, and the average of the carbon will be 0. Average of the carbon will be 0. So these kind of finding the oxidation number, perfect oxidation number is done with the structural identity if you know. If you take carbon suboxide for example, C3O2, what is the oxidation state of carbon? I am giving X, 3X plus -2 into 2 equal to 0. That is 3x minus 4 equal to 0, x equal to 4/3. This is correct. This value is perfect, but this is called the average oxidation number. Average oxidation number. What is the actual oxidation number? Actual oxidation number you can find out by the structure. You see, this is carbon suboxide. This is carbon suboxide. And how to find the oxidation number of the species oxygen -2, carbon +2. This is AA, no contribution. This is AB, this is -2, this is +2. AA 0. So the central carbon is 0. These two terminal carbons are +2 each. So the average will be +2 +0 +2/3. You are getting 4/3. That is perfect. It is average. Actual oxidation number will be the two terminal or the central carbon 0 and the other two carbon are +2 each, like that. So try to find out the oxidation number of as many species as possible. As many species as possible. Okay, try to work out the oxidation number. Try to incorporate the complex molecules also. Try to incorporate in your practicing complex molecules also. Fe4, FeCN 6 times thrice. What is the oxidation number of iron? The so-called Prussian blue. What is the oxidation number of iron? There is one iron outside the complex sphere, one iron inside the complex sphere. How do you find the oxidation number? Very, very simple. Very, very simple. You see, this is when you have a formula A4B3. What do you understand? This 3 is the charge of this and 4 is the charge of this. So naturally this 3 is the charge of this. So this iron is +3 state. And this 4 comes for the entire complex, 4 minus. So the entire complex region, it is 4 minus, while this ion is 3 plus. So the ion outside the coordination sphere, that charge is available here, 3 plus. And this entire coordination entity, the charge is 4 minus. So what is the charge of this ion? Now you can easily find out. Now you consider only this much part. So iron, I am giving X plus cyanide, you know, minus 1. So it is minus 1 into 6 equal to the charge of the radical, 4 minus. So X minus 6 equal to minus 4 and X is equal to plus 2. So this iron is plus 2 state. So iron outside the sphere, iron outside the complex entity, it is iron 3 plus ferric in nature. Iron inside the complex entity, it is ferrous in nature. We call it as ferrocyanide. Ferric ferrous cyanide. The very popular molecule iron 3 hexacyanidoferrate 2, Prussian blue. So try to incorporate these kind of examples also in your practicing session for the finding of oxidation number. So what is oxidation, what is reduction, what is redox reaction, what is non-redox reaction, what is reducing agent reductant, what is oxidizing agent oxidant, what are the types of redox reaction, and how to find the oxidation number. That is what so far we have seen. Right? Now, a very important topic that is dealt in this area, and of course we are applying in the 12th standard topic electrochemistry, that is regarding standard reduction potential. That is regarding standard reduction potential. Standard reduction potential. What is meant by standard reduction potential? This refers to the potential that a value experimental data indicating the tendency of a species to undergo reduction. That is standard reduction potential. It is evaluated by using standard hydrogen electrode, and there is a series called the electrochemical series. Electrochemical series. That means a tabulated arrangement of the standard reduction potential of various species in a regular order. That is called a electrochemical series. If it is available in the NCERT, I can show you. These are the preliminary area which we were going through. You may refer the textbook thoroughly on this context. Now I was talking about standard reduction potential. Let me see whether the table is available. Yeah, this is the table. This is standard reduction potential table. Electrochemical series, known to all. Now, what is this? Arrangement of standard reduction potential of various species in the order, and the reference one is SHE. This is called SHE, standard hydrogen electrode, whose potential is arbitrarily fixed as 0. And any species having higher reduction tendency than this are incorporated on top of this, and those species having a lower reduction potential are plotted below this. So these are lower reduction potential, that is having a negative data, while these are higher reduction potential that are having positive data. For example, F2 coming on top in the list. So F2 converted to F minus, the potential is 2.87. What does that mean? It is with reference to SHE. F2 plus 2 electron giving 2 F minus. The potential is E0, potential is plus 2.87 volt, high value, maximum positive value. What does that indicate? The tendency for F2 to undergo reduction is maximum. This has got a maximum tendency to undergo reduction. That means F2 has got a great tendency to undergo reduction. That is evident from this data. Therefore, this is a powerful oxidizing agent. This is a very good oxidizing agent. So anybody undergoing easy reduction, that is called an oxidizing agent, right? So that is the conclusion we get from this data. If you have a high positive figure, that species will be undergoing easy reduction and it acts as a very good oxidizing agent. So it is written like this: E0 F2 bar F minus, E0 F2 bar F minus, having plus 2.87 high positive value. That means this species has a great tendency to undergo reduction, and this is a very good oxidizing agent. Got it? And this is stable. This is relatively stable, and that is a weak reducing agent. That is a weak reducing agent. So I repeat, if you have a high positive value of standard reduction potential, that indicate this species, the species given on the left hand side, it's always conventionally written like this, right? According to IUPAC convention, standard reduction potential written in the reduction format. So E0 F2 bar F minus, high positive figure, means F2 is easily converted to F minus, and F2 is a powerful oxidizing agent. So let us have a hypothetical conclusion. E naught X bar Y, high positive value. What does that indicate? What does that indicate? You are comparing with somebody else. What does that indicate? This is easily undergoing reduction, and this is a very good oxidizing agent, and this is stable and a weak reducing agent. That is the point. Is it clear? Is it clear? Because it has got a very high reduction potential. Then what about the opposite scenario? What about the just opposite scenario? Suppose we are taking the reaction Li plus plus electron giving Li, as you can find from the textbook. Li plus plus electron giving Li, it is minus 3.05. What does that mean? The E0 potential is minus 3.05 volt. What does that mean? That means this reaction has got a least tendency to occur. This reaction has got a least tendency to occur. That is the meaning. That is the meaning. Rather, there is a great tendency to occur this reaction. Li is converted to Li plus plus electron. This reaction has got a great tendency to occur. This reaction has got a least tendency to occur. This reaction can take place easily. While, see, the potential for this is this. That means E0 potential for this will be plus 3.5. Opposite reaction means EMF will be positive. Potential will be positive. So what the conclusion is, this undergo easy oxidation. Therefore, this is a powerful reducing agent. Li is a powerful reducing agent. So let us see the conclusion. E naught Li plus bar Li minus 3.05. That means a high negative figure. High negative figure. Then the conclusion will be, this is easily oxidized to this. Just opposite to what we have seen here. This is easily oxidized to this. Therefore, this is a very good reducing agent. And this is relatively stable, and it is a weak oxidizing agent. Let me tell you hypothetically, E naught A bar B, high negative. What is the meaning? E naught A bar B, high negative. What is the meaning? The meaning is this B is easily oxidized to A, and B is a powerful reducing agent, and A is highly stable, and A is a weak oxidizing agent. That is the meaning. Now you can get this picture from the diagram also. You see the increasing strength of oxidizing agent. Increasing strength of oxidizing agent. You see, increasing strength of oxidizing agent. This is a powerful oxidizing agent. This is next. This is next. This is next. You see, I was highlighting the halogens. Permanganate, powerful oxidizing agent. Dichromate, very good oxidizing agent. Now, what about reducing agent? Increasing strength of reducing agent. This is a powerful reducing agent. Alkali metals are powerful reducing agents, while F minus is a weak reducing agent. Cl minus is better reducing agent than F minus. Br minus is better than Cl minus. I minus is powerful reducing agent among halides. Among halides, I minus is a good reducing agent than Br minus, than Cl minus, than F minus. It goes like that. This is a picture that we get from the standard reduction potential. You must try practicing the conceptual questions based on electrochemical series and its applications, which is coming as a continuation for the 12th standard electrochemistry also. So learning this context is very important, right? So various redox reactions, various types of redox reactions, finding the oxidation number using the traditional method and bonding representations, and then the reactivity series, electrochemical series. Probably the last topic from the chapter, as I was commenting, it's a very small chapter. The last portion from the chapter is balancing of chemical equation. Balancing of chemical equation. That is one last topic from the chapter. Balancing of chemical equation. Balancing of chemical equation. That's an important topic from the chapter, right? They will give you a skeleton condition and ask you to balance the equation, right? There are several methods adopted, half reaction method, ion electron method. That doesn't matter. That doesn't matter. Ultimately, when a skeleton is given to you, you must be able to balance it. Right? That may be asked in different media. That may be asked in different media. Right? Let's see how to balance it. I will take few examples and explain. I will take few examples and explain. What are the steps involved? Suppose a skeleton given to you, MnO4 minus permanganate oxidizes Fe2 plus to Fe3 plus, and itself it is converted to Mn2 plus in acid medium. This is a skeleton given to you. This is a skeleton given to you. How do you balance it? Permanganate oxidizes ferrous to ferric in acid medium, and itself it is reduced to Mn2 plus. Balance the reaction. Let's see what are the steps involved in balancing. Number one, identify oxidation and reduction. Number one, identify oxidation and reduction. What is oxidation? This is oxidation. Everyone can easily understand. Identify N factor. What is N factor? N factor means the total electron gained or lost. That is called N factor. Here it is oxidation. How many electron lost? That is oxidation. That is N factor. And it's easy to understand the difference in this number will be N factor. So 2 become 3 means N factor is 1. So oxidation, N factor is 1. Now go through reduction. Reduction, permanganate, manganese is plus 7 state and is reduced to plus 2 state, and this is reduction. In permanganate, manganese is plus 7 state and is reduced to plus 2 state. That is reduction, right? What is the N factor? What is the N factor? Plus 7 changes to plus 2. N factor is 5. So here you can understand what is oxidation, what is reduction, what is N factor. Oxidation, N factor is 1 and reduction, N factor is 5. That means during oxidation, 1 electron is lost and during reduction, 5 electrons are gained. That means it is an unbalanced scenario, because number of electron lost and gained must be equal, because oxidation and reduction goes hand in hand. The number of electron lost must be equal to number of electron gained, and hence it is an unbalanced chemical equation. How to balance it? Very simple procedure, known to many of you. What do you do? What do you do? It is just cross multiply oxidation with 5, and here multiplying with 1, which is not meaningless. I mean, no meaning to comment that, because it is same. So oxidation reaction you can multiply with 5, right? So that number of electron will become 5 here, and already it is 5 here. So what do you get is the new skeleton, I mean the new equation. It becomes MnO4 minus plus 5Fe2 plus. You get 5Fe3 plus plus Mn2 plus in acid medium. This is the electronic balanced equation. Now the electrons are balanced. Now the electrons are balanced. Now the second step is another important one, that is to balance the charge. In an ionic reaction, we need to balance the charge. How to balance the charge here? How to balance the charge here? Charge can be balanced using H plus if the reaction is in acid medium, using OH minus if the reaction is in basic medium. So charge balancing, if the reaction is in acid medium, it is balanced by H plus. It is using OH minus if it is a basic medium. In basic medium, charge balancing done by OH minus. In acid medium, charge balancing done by H plus. Okay, so this is an acid medium. So what do you do? In acid medium, how it can be done? Using H plus you can balance the charge. Sir, how to balance the charge? Very simple. Look at this. On the left hand side, how many charge? You have minus 1 charge here, and 5 into 2 plus 10 charge here. So minus 1 and plus 10. So the total charge here is plus 9 on the left hand side. What about on the right hand side? Right hand side, 5 into 3, 15 positive charge and 2 positive charge. So it is 15 plus 2, total 17 positive charge. I repeat, 5 into 2, 10 and 1 minus. So it is 9 positive charge on the left hand side. Here 17 positive charge on the right hand side. So this we need to balance. This we need to balance using H plus. So how many H plus on what side? You can balance it. How many H plus? That is to be given on which side? There is positive charge deficiency here. How much? How much? 16 positive charge is deficit, isn't it? 16 positive charge is deficit, or how much? 19, sorry, 9 there, 17 here. 9 and 17, that is the difference. How much difference it is? 8 positive charge. 8 positive charge deficient there. 17 positive charge here and 9 positive charge here. Right? So 8 positive charge deficiency on the left hand side. So what you can do is add 8H plus on the left hand side. Rewrite the equation. You can rewrite MnO4 minus 5Fe2 plus 8H plus giving 5Fe3 plus and Mn2 plus. You can verify. You can verify. 5 into 2, 10 positive charge, 8 positive charge, 18 positive charge, 1 minus 17 positive charge. Here it is 5 into 3, 15 plus 2, 17 positive charge. Now the charge balancing is done. And the balancing of equation is almost over. And now the last step, balancing of hydrogen or oxygen. Balancing of hydrogen or oxygen. If you balance hydrogen, automatically oxygen is balanced. If you balance oxygen, automatically hydrogen is balanced. Right? See how to balance it. How to balance it. Here we have 8 hydrogen and right hand side we don't have any hydrogen. Over. You can add 4H2O on the left hand side. You get MnO4 minus plus 5Fe2 plus 8H plus giving 5Fe3 plus Mn2 plus 4H2O. You can very well confirm the reaction is entirely balanced. The reaction is entirely balanced. Right? What are the steps involved? Identify oxidation, identify reduction, identify N factor, balance the N factor by cross multiplication. Next step, identify the charge difference, balance charge difference using H plus if the reaction is commented in acid medium, using OH minus if the reaction is commented in alkaline medium. Balance the charge. Last step, balance for hydrogen or oxygen. If you balance hydrogen, automatically oxygen will be balanced. If you balance oxygen, automatically hydrogen will be balanced. Right? Now we will take another example from basic medium. We will take another example from basic medium. Let us take an example from basic medium. If some example if I am getting from NCERT, it will be well and good. Yes, we have an example from basic medium. This one I will take for discussion. This one I will take for discussion for explaining basic medium. How to balance in basic medium? We have the skeleton given. I have taken the equation from NCERT, right? So the skeleton equation which you have taken from the NCERT, permanganate plus I minus giving MnO2 plus I2. Let's see how to balance it. So it is MnO4 minus plus I minus giving MnO2 plus I2. So here manganese plus 7 reduced to plus 4. This is reduction. And N factor, simple to understand, 7 to 4, it is 3. Okay. Now, I minus converted to I2, naturally you can give 2I minus. 2I minus can only give you I2. So, I minus 2, I2 0, that is oxidation, N factor will be 2. For one iodine, N factor is 1. There are 2 iodine, only can give you I2. So, it is N factor 2. So, the point is oxidation N factor 2, reduction N factor 3. It is an unbalanced scenario. How to balance it? Step 1, cross multiply or do suitable mathematical manipulation so that the number of electrons in oxidation and reduction becomes equal. So, how do we do? This is multiplied with the 3 and this is multiplied with the 2. So, the formula will be 2 MnO4 minus plus 6 I minus giving 2 MnO2 plus 3 I2. Now, the electronic balancing is over. The N factor balancing is over. Now, the most important one is an ionic reaction. We need to balance using OH minus as it is done in basic medium. The reaction is occurring in basic medium. So, balancing of charge to be done using OH minus. So, what is the charge over left side? This is basic medium reaction. What is the charge on left hand side? 2 minus and 6 minus. So, it is minus 8 on left hand side. What about right hand side? Right hand side it is 0 charge. So, left hand side there is 8 minus charge. Right hand side there is 0 charge. Let us verify once again. 2 minus 6 minus 8 minus 0 0. So, using OH minus you can balance the charge. So, how many OH minus on what side? How many OH minus on which side? We need to give 8 OH minus over the right hand side. So, you need to add 8 OH minus on the right hand side. So, the new formula will be 2 MnO4 minus plus 6I minus giving 2 MnO2 plus 3I2 plus 8 OH minus. Now the charge is balanced. And the final step will be balancing hydrogen or oxygen. So how to balance hydrogen or oxygen? Here you have 8 hydrogen on right hand side. So you can give 4 H2O on left hand side. So it will be 2 MnO4 minus plus 6I minus plus 4 H2O giving 2 MnO2 3 I2 plus 8 OH minus. You can verify it will be a balanced formula. Balanced stoichiometry. So what all things we did once again? Identifying oxidation, N factor, identifying reduction, N factor. Now do suitable mathematical manipulation to get the N factor equal. So reduction reaction multiplied with the 2, oxidation reaction multiplied with the 3, we got the electronic balancing done. N factor is balanced. Now the charge balancing using OH minus as the reaction occurs in basic medium. And finally balancing for hydrogen and oxygen. If you go through the textbook, you can find it is done by half reaction balancing. Two half reactions taken separately, balanced separately, and then added. So either way, whichever way you proceed, that doesn't matter. A skeleton given to you, are you able to balance or not? I will take one more example to wind up the chapter. Let me see some suitable example we get. We have a beautiful example here. We have a beautiful example here. That is this one. That's a disproportionation. That's a disproportionation reaction. Let us discuss that. A disproportionation reaction. Another example taken from the NCERT text. White phosphorus in alkali medium disproportionate to pH3 and HPO2 minus. Please understand this, such a species does not exist. That's a mistake. That's a mistake. In the textbook itself, that's a mistake. Such a species does not exist. What is the original skeleton? It is white phosphorus in alkali medium. You are getting pH3 and H2PO2 minus. That is correct. This is hypophosphorus acid salt. Hypophosphorus acid H3PO2 can ionize as H plus and H2PO2 minus. Right? And it can only ionize once. It is a monobasic acid. Hypophosphorus acid is a monobasic acid. Even though there are 3 H we can find, only one hydrogen is acidic in nature. The 2 hydrogens are reducing in nature. So it can ionize only once. So the ionized salt should be H2PO2 minus, not HPO2 minus. There is no further ionization. It cannot ionize further. Anyway, this is the species. Now let us try to understand. This reaction is a typical example of disproportionation reaction. This is disproportionation reaction, where phosphorus 0 is reduced to -3 and oxidized to phosphorus here is +1. So phosphorus 0 reduced to -3 and oxidized to +1. So reduction N factor is 0 to -3, 3, and oxidation N factor is 0 to 1. It is 1. It cannot be accepted. It has to be equal. So how we can equalize in a disproportionation reaction? How we can equalize in a disproportionation reaction? You can apply some simple logic. You can apply some simple logic. See, number of electron lost and gained should be made equal. So what can be done is, this you multiply with the 3. So that here it will be 3. There is already 3. So what is a new skeleton becoming? What is a new skeleton becoming? P4 plus OH minus giving pH3 plus 3H2PO2. This way. Now you understand there are 4 phosphorus. Out of the 4 phosphorus, 3 phosphorus undergo oxidation, losing 1 electron each. So total 3 electron. And that 3 electron gained by the next phosphorus. See, there are 4 phosphorus. there are 4 phosphorus. Out of the 4 phosphorus, 3 phosphorus loses 1 electron each and become +1. And the 4th phosphorus accept that 3 electron and become P3 minus, phosphine. Right? Like that you can understand. So this is now n factor balance, phosphorus is balanced. Next is charge balancing. How to balance the charge? You look at right hand side, it is 3 minus. Right hand side there is 3 minus. So here you can give 3 minus. So charge is also balanced. So n factor is balanced, charge is balanced. By giving 3 here, now it is 3 on both sides. Charge is balanced. Now it is hydrogen balancing. Left hand side, how many hydrogen? Left hand side, we have 3 hydrogen. Right hand side, we have 3 hydrogen plus 3 into 2, 6, 9 hydrogen on the right hand side. So 3 hydrogen on left hand side, 9 hydrogen on right hand side. That means a difference of 6 hydrogen. A 6 hydrogen deficit on the left hand side. 6 hydrogen deficit on the left hand side. So you can add 3H2O on left hand side. So the formula will be P4 3OH minus 3H2O giving PH3 and 3H2PO2 minus. It is a completely balanced equation. 4 phosphorus, 3 plus 1, 4 phosphorus. Hydrogen, 3 hydrogen, 6 hydrogen, 9 hydrogen, 3 hydrogen, 6 hydrogen, 9 hydrogen. Oxygen, 3 oxygen, 3 oxygen, 6 oxygen, here also 6 oxygen, everything balanced. That is an example for disproportionation reaction, how to balance it. So try to take as many examples as possible to practice yourself for understanding the logic of balancing of chemical equation. As many examples as possible, including the advanced level exercises. Okay, that is the last topic from the chapter. So far, how many area we have gone through? What is redox reaction? What is oxidation reduction? What is oxidizing agent? What is reducing agent? What are the various types of redox reaction? Synthesis type, combination type, decomposition type, metal displacement, non-metal displacement, disproportionation, syn proportionation, com proportionation, various variety of redox reaction. Then calculating the oxidation number, traditional way of finding the oxidation number, bonding method to finding the oxidation number, then standard reduction potential, electrochemical series and its application. Which one will act as a strong oxidizing agent? Which one will act as a strong reducing agent? How can you correlate with the data given? Right? And finally, balancing of chemical equation. Various steps involved in balancing of chemical equation. Fundamentally, the important steps are identify oxidation, reduction, balance the N factor. Number 2, if it is an ionic reaction, balance the charge. Using H plus if it is an acid medium, using OH minus if it is an alkaline medium. And finally, balance for hydrogen and oxygen. Right? This is the topics that is available or to be importantly gone through from the chapter redox reaction. As I said, a very small chapter. With another video, we will meet with another class, another chapter. Okay, that was the rapid revision for redox reaction in this session. Okay, bye, see you, take care.